Hey everyone, welcome back to my house. So today, as promised, we're going to finish up general linear models. And in particular, what we're going to be doing is what is traditionally referred to as a factorial model. As I've repeated before, these are all linear models, and we're using ANOVA to do hypothesis testing on these linear models. So just like regression and multiple regression and COVA. Factorial models, as we'll see, are the same thing. Really what Factorial is describing is the experimental design. And the experimental design for a factorial design is one where you have more than one factor in the model, and the treatments for those factors are perfectly crossed with one another so that all possible combinations of the experiment are included in the design. So Factorial is really much more about the experimental design than it is about the analysis, because the analysis is the same. So let's shrink me down as much as possible, and we can take a look here at what we're going to play with. I'm going to make up some data here, and we are going to pretend that what we have is we have three different treatments. I'm calling them treats to be cute. Let's pretend that they're diet items. We have two different temperatures, high temperature and low temperature, and then we have the masses of the organisms that were being raised there. In my brain, I always end up reverting to thinking about raising caterpillars. And so here we're comparing three different diets for these caterpillars in an experimental grouping where there's a high temperature and a low temperature treatment, and we're looking at the mass after a certain amount of time. And this over here is what the data might look like if you were to read it into, say, from Excel or something like that. And to show that it's a balanced design and that all possible combinations are included, I'm going to use this function called table, and I'm going to put treats and temperature in there, and it's just going to give me the number that's occupied in all those combinations. And so here I have a nice little balanced design where I have 5 in treatment A at a high temperature, 5 in treatment A at a low temperature, 5 in treatment B at a high temperature, so on and so forth. So in total, each of the different treatments has 10 replicates each, and temperature has the total of 15 replicates for each of those two treatments. In total, we have 30 replicates. And so the idea with a factorial design is that we can start looking at combinations and understanding, first of all, it can be more efficient, so we don't have to redo experiment a bunch of times with a lot of replicates, but we can understand how things might interact with one another when trying to come up with a model that can effectively make a prediction. So much like we did with the ANCOVA example, we can go ahead and we can make just a simple model. And here I'm just going to say the treatments and temperature are going to predict mass. And I'll go ahead and I'll run that model, and I can run an ANOVA on that model. And what do I conclude from the hypothesis testing part of this? Well, I would conclude that treatments seem to be important. They should be included in the model, but temperature is not. And so let's look at exactly why that might be happening when we actually look at our data. So I'm going to just throw up some plots here. Let's see here. I'm going to make a box plot. And we will open this window up a little bit more, and we will open that up a little bit more. Okay, and so here's my treatment A, B, and C on the high temperature group, and here's treatments A, B, and C on the low temperature group. And I can go ahead and I can plot out the mean for the high temperature group across all A, B, and C, and the mean from the low temperature group across A, B, and C. And just by looking at where these means are falling out, it shouldn't be terribly surprising that when we ran the ANOVA, that it concluded that temperature is not an important predictor in this model. Likewise, I can reorganize the box plot. And so now I have treatment A here, and then treatment B, and then treatment C with high and low temperatures next to one another. And now we can think about what is the hypothesis that's being tested for the different treatments. And again, what I'll do is I will plot the means. So this is the mean of A across both temperatures. This is the mean of B across both temperatures. And this is the mean of C across both temperatures. And eyeballing this, we can see, well, maybe it makes some sense that the ANOVA was picking treatment up to be important and should be included in the model, just given by the fact that we can eyeball those means and see that those means are different from one another. So that's all fine, but what that's assuming is that we have additivity, meaning that we expect that the effective temperature to operate separately from the effect of the treats. And we don't really have any reason to expect that. And so what we might want to do is we might want to test for that. And so we test for that by setting up a model that includes the interaction. So here I have set up a model that includes the interaction. I have treatment plus temperature plus treatment by temperature. This is the longhand way of doing it. Again, this would be the shorthand way of doing it, and you would get the exact same model if you just say treats times temperature. That's telling R that we want to explore that interaction term, but those main effects, those effects that are not involved in an interaction, or the terms that are not involved in the interaction, will still be included in the model. So I'll go ahead and I'll run this, and I will go ahead and I will do an ANOVA on my mod interaction. And what do I find out when I do that? What I find out is that treats are still showing to be significant. Temperature is still showing to not be significant. And again, those plots that we looked at, that makes sense. But now when we look at that interaction term, the treats by temperature, it is saying that there is a significant interaction term. As soon as we have a significant interaction term, that's telling us that we are not allowed to interpret the statistical hypothesis testing on our main effects, which means that we can no longer trust that temperature is not important. And potentially we can no longer trust that treatments are not important, okay? But the main thing here is that we cannot really trust that part of the hypothesis testing. And so we can explore what this might look like and what might be driving this interaction term. And although these box plots are kind of nice to look at the summary of the data, a lot of times it's kind of hard to draw your eye, and I had to draw two different box plots. And there's an easier way that we can look at how the interactions might be driving this, and that is to use a built-in function called interaction plot. And interaction plot, as the name implies, will draw what's called an interaction plot. So the arguments that we're going to be concerned about are x factor. This is going to determine what are the terms that are going to be defined by the x-axis. And so for our purposes here, let's make it temperature. Oh, I didn't mean to do that. I meant to do this. Equals. It's an argument. Okay. So that's our x factor. Next, we need our trace factor. Those are the things that we're going to plot and keep separate from one another. What I mean by that will be clear in just a second. But I'm going to go ahead and I'm going to say trace.factor equals treats. And then I have to give it a response variable. The response variable is mass, because that's how our data are set up. So I go ahead and I do that. And this is what an interaction plot is. So note that here we have a legend that's telling us treatment B, treatment C, and treatment A. So here's the effective here's treatment A at a high temperature. Here's treatment A at a low temperature. Here's treatment, or I'm sorry, that's treatment B at a high temperature, B at a low temperature, A at a high temperature, A at a low temperature, and C at a high temperature, and C at a low temperature. So just by eyeballing that, we can see how that interaction term might have been significant, because we can kind of see just by looking at this that that clearly there's a different effect, for example, between high and low temperature on treatment C compared to treatment B, or at least it certainly looks that way. It looks like they're responding differently to those temperatures. So we can think again about when we're comparing just the temperatures. Those are the means that we're comparing, and so it might make sense that we are not getting a significant interaction term. I'm going to make the same interaction plot, but this time for the x factor I'm going to use treats, and for the trace factor I'm going to use temperature. It's just another way to look at the same data, so we can just kind of explore what might be driving that interaction term. So I'll go ahead and do that. So now our x-axis has our treatments, and now we have this key here. This is low temperature, and this is the effect of high temperature. And again, thinking about when we were doing the hypothesis testing on those main effects, those are the means that we're comparing. So those big red dots are the mean for A, the mean for B, and the mean for C. across both temperatures. And so what we'll want to do is we'll want to split these models apart into two separate models, or into multiple models, to understand and to accurately make hypothesis testing. So let's go back to our first interaction model, and again remind ourselves that this is telling us the temperature is not important. And so let's split up the analysis based upon that, and let's think about the importance of treatments, because that's what we might be interested in. So I'm going to split this out, and what I'm going to do is I'm going to have a high mod and a low mod. So I'm going to be taking just temperatures that are super duper equal to high in this model, and I'm going to do mass being some function of treatment, and then I'm going to do the same thing here. This is just going to call out those mass values where temperature is super duper equal to low. And so let's go ahead and we'll run those ANOVAs. So there is my ANOVA on the high mod. Scoot that back here. And sure enough, when the temperature is high, there is a significant difference among treatments. And now let's look here when temperature is low. And aha, we have failed to reject the null hypothesis that that there is no effect of treatments. Which means that if we were to go back and look at our main ANOVA that included the interaction term, we would be erroneous to say that treatments are significant, because it turns out that the treatments are indeed significant, but the diet, the treats, they only matter at a high temperature. At a low temperature, it doesn't matter what diet you're on. So if you had just interpreted your main effects of that ANOVA, you would have been wrong by saying that, oh, those diets are always different from one another, because it turns out that those diets, those treats, are only different from one another when you are also crossing that with a high temperature. You lose that effect at a low temperature. So let's do the same thing. Let's look at the other interaction plot so we can understand even more what's happening. So here is our interaction plot now where treatments are our X factor and temperature is our trace factor. And once we have that, we might want to now separate out a model where we're going to do one for each treatment to see whether or not temperature actually matters. And so I've already done that, so I will cut and paste it into our little window of discovery here. Okay, and so again, what I'm doing with the code here is I'm saying that I'm only going to include mass where treats is super duper equal to A, and I'm only going to take temperatures where treats is super duper equal to A. And so what this is going to set up, I'm removing treatments from all of these models now, because each model is only going to have one treatment, but I'm going to be able to explore the difference between both temperatures, okay, the high and the low temperature. And so let's go ahead and we'll do that. So here we are in treatment A, and sure enough, there is no effect of temperature on treatment A. On treatment B, there is no effect of temperature on treatment B. Treatment C, there is an effect of temperature on treatment C. Okay? So again, we would have been wrong if we go back to our original model and interpreted these main effects, because if we had interpreted these main effects, we would have said, oh, there's a real strong effect of treatments. But we actually now know that treatments aren't important across both temperatures. They're only important at one of the two temperatures. And likewise, we would have been wrong to say temperature plays absolutely no role. Temperature is not important. That's clearly not true, because if you happen to be feeding on diet C, then temperature is important. And it is an important predictor. And so if we go back to our interaction plot, what we're picking up is this difference here, is that when you are at a high temperature on diet C, you are predicted to weigh less than if you are at a low temperature on diet C. That's what that's picking up. So it would have been wrong for us to conclude that there is no effect of temperature. Okay, I hope that that makes some sense on why we have to be really, really careful about thinking about always including those interaction terms and making the assessment as to whether or not we feel comfortable with the hypothesis testing. And although this might seem like it's kind of cumbersome to do it this way, this is really the only way that you can do this type of hypothesis testing on a general linear model when you have a significant interaction term. So always be aware that the significant interaction term is the important thing that you're going to need to deal with if it's there. If there is no significant interaction term, you can go ahead and you could analyze your main effects and in a single analysis of variance framework. It's only when you have that significant interaction term that you have to start breaking things apart in order to do the statistical hypothesis testing. And I'm being explicit about the whole idea of only worrying about it's only important for the statistical hypothesis testing portion because we still have a model that included that interaction term. And again, we don't trust that, but our model is just fine. We still have a model that has parameters. Those parameters are going to do a good job, hopefully, at helping us determine what the predicted value is for each of those different treatment combinations, right? And there's 6 different combinations. So this model that we have right now will predict how much you weigh on diet A at a high temperature, how much you weigh on diet A at a low temperature, diet B at a high temperature, diet B at a low temperature, high, low, whatever, all 6 different possible combinations. And so let's remind ourselves how we can use these coefficients. And so if I were to look at my model matrix, let's remember that behind the scenes, everything is dummy coded and everything ends up being just a big old regression. Okay, so here's our dummy coding. I'll even make this bigger so we can see it on one little loop. There it goes. And so these first 5 rows here, those are the individuals that are on diet A, and they are those individuals that are at a high temperature. So remember that because we're dealing with a cell means model, we are going to take the lowest level across factors as being the intercept. So in this case, the intercept is going to be the mean of an individual on diet A or treats A raised at a high temperature. And again, that's just because what computer programs like R and others do is they order the factors alphabetically. So obviously A comes before B and C, so A is going to be part of the intercept. And then high comes before low because the letter H comes before the letter L in the alphabet. So it does things alphabetically. And so that means that if you are on treatment A and you are at a high temperature, your expected value, the mean for that is what the intercept is. And so we can go ahead and prove to ourselves that that indeed is the case. And so I'm just going to say, what is the mean of treatment A at a high temperature? So I will go ahead and I'll do that right here. Again, I'm just saying, I'm calling out the index, which treats are super duper equal to A, and which temperature is super duper equal to high. And I'm going to run that, and I'm going to run that without getting all those warnings. And that's the mean of that group. If we look at our model, that is the intercept. So indeed, that means that everything else, all the other combinations, are all going to be measured relative to an individual that was on treats A and at the temperature that was high. And so just by looking at these parameters, then we should be able to interpret now enough to have some expectation. So if I'm at a high temperature and I'm on treatment B, I expect to weigh 3.1138 more than 18.8951. And so we can prove that to ourselves by taking the mean for those ones that are in treatment B at a high temperature. I get 22.0089, and sure enough, that is going to be that plus that, and that's where that number comes from. And so remember that this whole, am I going to include things or not, that's all that the dummy coding is doing. So we can think about this dummy coding as being a bunch of switches that we're switching on and off. And so we have our model, and we have the parameter estimates of our model. Let's look at the model again real quick. That, and then that. Okay, so here's our parameter estimates, and then here's our model matrix that shows what our dummy coding is. So again, if you're in the very first group, treatment A, and you are at a high temperature, you're going to get the intercept, which is their mean, times 1. You multiply 1 by something, it doesn't change. But then you're going to multiply all of these other coefficients by 0. So essentially, they're just totally dropping out of the model, and that's going to be our baseline. If you, for example, are in treatment B, well, this is where the one with treatment B starts. So that is the dummy coding for the treatment where you are on treatment B and you are at a high temperature. That is going to include this 18.8951 plus 3.1138 plus all the others, but all the others are going to be multiplied by 0. And so that is all that we're doing when we're doing the dummy coding. And in the code that I've posted, I've actually done that in a very long, cumbersome way, because that's sometimes how I do things. So again, here's our mean, where here's the mean mass when treatment's A and temperature is high. And that is our intercept for the model. And then what we can also do is we can pop it right into our linear model. So here I have put it right into our linear model, and here's my dummy coding. So it's going to be the intercept times 1, and then it's going to be all these other coefficients times 0, times 0, times 0, times 0. And sure enough, that is the mean at 1. And I could go back through and I could do it with others. So let's say now we have treatment B at a high temperature. And so if we were to go back and look at our dummy coding, what we would find is that, first of all, once again, everybody gets the intercept. And now we're going to multiply this coefficient, which is the slope for treatment B, by 1, which means now its switch has been turned on and it's part of the model. Everything else here is dropping out because all those coefficients are multiplied by 0. And so let's take a look. How does our model do? We have treatment B at a high temperature. That's the actual mean based upon the convoluted code, or we can use our linear model, and our linear model is giving us the exact same answer. So it seems like it's working out pretty well for us. And again, let's do the same thing here now, where we're on treatment C at a high temperature. And if I do that, what do I find? Again, everybody's going to get the intercept. We're dealing with treatment C now, so we're going to get rid of that coefficient for treatment B. Again, we can look at those different coefficients. So we're going to get rid of that coefficient for treatment B, but now we're in treatment C. So we're going to multiply this coefficient by 1, which means that that switch has been turned on. It's going to be included in the model. We're not at anything to do with a low temperature yet, so all of those are going to be multiplied by zeros. They're going to drop out of the model. So we go ahead and we run that. We get 15.89, which is the mean for treatment C at a high temperature. So now let's take a look really quickly at if you're in treatment A, which again is our intercept, at a high temperature, but what if you're in treatment A at a low temperature? And so let's go ahead and let's pop that into our linear model, or into our linear model. No. Okay, so again, here's our coefficients over here on the left. And so what do we have? Everyone starts with the intercept. Everybody starts out as being in treatment A at a high temperature. It's not in treatment B, so we're going to multiply that by a 0. That drops out because of the dummy coding. We're not in treatment C, so that's going to drop out right there. But we are now at a low temperature. And so we're going to include now that parameter in the model. We are not in treatment B at a low temperature, so that's going to drop out of the model. Here's our 0. And then likewise, we're not in treatment C at a low temperature, so that's going to drop out of the model. And so now again, all we've done is by using those zeros and 1s with dummy coding is we are basically using them as switches to turn things on and off. And so let's see, our linear model predicts that the expected value, if you're in treatment A at a low temperature, your expected value is 18.16, and the actual value for that is, lo and behold, 18.16. So our model is doing a pretty fantastic job of explaining those differences. And I'll just grab one more. So I'm doing 5 out of the 6 possible combinations, just, you know, trying to be really efficient with time here. So now we're dealing with a situation where we're in treatment C and we're at a low temperature. Let me go back up here and do that so we can look at our parameter estimates. So again, everybody starts out as treatment A at a high temperature. Everybody gets the intercept. So we're going to multiply that by 1 based upon our dummy coding. We are not in treatment B. So treatment B, which is right there, that is going to get dropped out of the model because we're putting a 0 there. We're turning that switch off. We are in treatment C. So we're turning that switch on with that little 1 there. And that means that right now, as we're progressing through this linear model, we are now negative 2.996 less than 18.8951, which is what the expected value is for treatment C on a high temperature. But now we're dealing with a low temperature. So we have to go through here and think about these things here. Now we have temperature low. So yes, we are at a low temperature. So we'll turn that switch on, which is right here. And then finally, not only are we in temperature low, but we're not treatment A on temperature low, we're treatment B on temperature low. So we're also going to include this parameter in the model. Or I'm sorry, we're in treatment C on temperature low. So we're going to include that temperature into the model, and we're dropping out temperature treatment B, or temperature low treatment B. And so again, it's just a matter of turning on and off all of these switches that are involved with our factorial design. There are 6 possible combinations, and all we have to do is know what switches to turn on and off, and we will get the expected value. And so there we have it, 18.6266, and that is the actual value for treatment C at a low temperature. And so the reason why I went through all of this kind of long process of showing all this is, again, to emphasize that we're building models. Our hypothesis tests are really about like thinking about the importance of various things in the models. But at the end of the day, our modeling efforts are all about estimating parameters. And we feel pretty good about our parameter estimates if we do a good job at predicting our own data, and that we can learn something about the magnitude of the effect. And we can also learn something maybe interesting about the underlying biology, like why does temperature matter on diet C but not on the others, which could then lead us to looking at further types of experiments. And so again, the important thing is interpreting the parameters as well as doing the hypothesis testing. The hypothesis testing is fun and it's interesting, and people certainly always like to see their p-values, but let's never lose sight of the fact that what we're doing here really is we're building model. And I also wanted to point out, by doing this convoluted, this long kind of thing where we went through all the model, that even though the hypothesis testing wasn't valid because we had that significant interaction term, the model itself was great. It predicted things absolutely fantastically. And we would stick with that big model if we wanted to predict something, if we had future data come in. But when it comes to the hypothesis testing, we have to split them up so we can understand what's driving that significant interaction. And so briefly, to complete then this, I want to think a little bit more about different scenarios where you might have certain expectations as to what might be happening when you're looking at a simple type of factorial ANOVA like we've been playing with here, and in particular when you are thinking about what might be driving those significant interactions. And so to do this, I'm going to just make some cartoon, make a cartoon that will, I got to find my quartz window. Well, some things never change. Okay. That will basically replicate those interaction plots that we were looking at, but it'll just be my cartoon version of that. And so I think what I'm going to have to do, so I don't go crazy, is I'm going to have to move some stuff out of the way here. Because although I can make my window float, R does not like there. Okay. So there's our blank screen, and now comes Jim's cartoon time. Let's see here. We're going to start here. Down at the bottom here, I got high and low, so that's going to be our high and low temperatures. I'm going to say that those are different treatments, okay? And then I'm going to put the results up here that you would expect to find based upon this interaction plot if you were dealing with an ANOVA table. So again, here's our 3 different treatments. I've color-coded them. So this is the mean for high temperature if you're in the red group. Green group, that's the mean at a high temperature, so on and so forth. And so we can look over here at what the expected results might be in an ANOVA table where our treatments are not significant, our temperature is not significant, but the interaction is. And again, this is going to be a great example of why you don't want to do the hypothesis testing on the main effects if you are only looking at, or if you're not considering the fact that you have a significant interaction. And so first let's look at why would we have no significance detected for high versus low temperature? Well, the mean of high is there and the mean of low is there. And so it wouldn't be surprising that temp would turn out to be NS, not significant. We can do the same thing to understand why we might have no significant treatment effect. So let's look at the mean for the red treatment. Treatment A, I'm calling it apparently. So A is there. The mean for B is there, and the mean for C is there. And so what's that giving us is that since we're looking across the mean across high and low temperatures, is that the means are the same across all of those treats. So there's no difference between treats. Now just looking at this plot that we've made here, we know that we would be probably wrong to walk away from this analysis saying no effect of temperature, no effect of treatment, because we would have that significant interaction term. And it might make sense that if we were to split them up, that maybe if you are in treatment B, the blue one here, that you're lower at a high temperature than you are at a low temperature. And likewise for treatment A, you're higher at a high temperature and lower at a low temperature. And then for treatment C here, there absolutely is no effect whatsoever of temperature on the response variable. And so this is like a nice illustration of why you always have to, as soon as you have that significant interaction term, you just got to stop and understand what's driving that significant interaction term, and certainly do not do the null hypothesis testing based upon the ANOVA of the full model that includes the interaction term if you have a significant interaction. And so here's another fun little scenario. Fun, Jim says. So here is an example of where we might expect the treatments to be significant, but temperature to not be significant, but the interaction term to be significant. And again, let's go through that and let's understand why. If we were to look first just at temperature, so why might temperature not be significant? Well, this is the mean of the temperature at the high group, and this is the mean for the temperature at the low group. They're at the same level. On average, between high and low temperatures, they're the same. It would make sense that temperature would not show up to be significant. We can do the same thing. Let's look at it across our different treats and understand why treats here actually looks like it should be significant. And so let's look at the average of the red group, blue group, and green group. And so now, you know, we're basing this mean over here on the average for group B, the blue group here, between high and low. And for A here, it's the average between the high and low of there. But the overall on average, A is greater than C is greater than B. Okay? But we also have this significant interaction term where I'm eyeballing this interaction plot, and what I'm assuming is that temperature probably is important, but it's only important at a high temperature. At a low temperature, they all converge at the same mean, so there doesn't seem to be any effective treatment whatsoever at low temperatures. So again, it would be erroneous for us to say that treatments are significant because they're only significant when they happen to be in high temperatures and not in low temperatures. So again, always important to carefully inspect what's happening once you have that significant interaction term. All right, let's do a couple more. There's the bagpipes again. All right, ooh, that was just a little too much. That's too much. Let's try that again. Okay, so now we have a situation where treatments are significant, temperature is not significant, and the interaction is not significant. Because the interaction is not significant, what that should immediately tell you, much like it did with an ANCOVA, is that these lines here, because remember, when we're doing these ANOVAs like this, we're just doing a bunch of regressions. These lines are perfectly parallel to one another, which means that there is no difference between high and low temperature, so we would expect temperature to not be significant. The lines are parallel to one another. We would expect there to be no significant interaction, but we might expect that indeed there is a significance among those treatments, because there is the mean of A, there is the mean of B, and there is the mean of C. Okay? And so in this case, if you had run this ANOVA model, you could simply interpret your main effects, and you could say, oh, okay, yeah, there is a significant effect of treatments. I'll also mention this. It is entirely legitimate if you have a non-significant interaction term, especially if it's profoundly not significant, and this is where that step function might come in and be handy, you can drop the interaction term from the model if you really think the interaction term is just wasting parameter space. A lot of times people don't like to do that because it seems kind of like you're cheating, and if you have enough replication, it probably won't make any difference. But just be aware that you can do that, because again, as I've said multiple times, it's your model. You can do whatever you want with your model. Okay, let's do one last example here, and this is going to be an example of where we have both treatments being significant and we have temperature being significant, but there is no interaction effect, right? There is no significant interaction. And again, we can eyeball this and understand what's happening at each step of the hypothesis testing. When we're doing the hypothesis testing for temperature, we're looking at the average across all treatments at the high temperature versus the average across all treatments at the low temperature. Those means look a little different to me, so we might not be surprised that in our ANOVA table, that's a significant main effect. Likewise, we could look at what's happening when we're doing the hypothesis testing on the treatments. So here's the means for those treatments, again, across both high and low temperatures. And we can see that A is greater than B is greater than C. And so this would be another example of where it would be totally fine to do the hypothesis testing on the full model, looking at the main effects, because you do not have a significant interaction term. And that a significant interaction term is implying that these lines are mirror images of one another. They're identical. They're not mirror images. They're identical to one another. The only thing that's changing is the elevation of those lines. So, okay, well, that wraps up our little foray into general linear models. As promised, what we will begin doing next week is general linear mixed models, which are just going to be slightly different in that we're going to start thinking a little bit more carefully about the error structure. And then once you get done with that, we can start now thinking very informed as folks that understand some statistics about experimental design and how we're going to go about doing that experimental design. So at that, I'm going to say farewell, and say farewell to general linear models. It's the last time we're going to, kind of be talking about them in their pure sense. Stay safe, stay healthy, and you'll see me next time I grace your computer screen.